Hi, good morning, everyone. Hope you had a restful weekend, and we're in week 4 already of the program, so things are progressing quite fast. I'm just gonna spend the first 20 minutes maybe to go through some of the application questions from lecture 2 and 3 first, and then we're gonna wrap up lecture 3 and probably going to start on number 4 as well. This is our schedule. Today is the 29th. So respiratory system is relatively straightforward and simple. We will definitely be able to finish it. Next week, we will have a test 1 review. I'll tell you a little bit about the lab quiz as well when more people shows up. And then our test is going to be next Wednesday. Okay, next Wednesday. And there will be no synchronous class next Wednesday. Okay. So these are the application questions from the study guide. And hold on, let me just fix the screen here. And no answers are in the answers that I post. Okay, I left them out on purpose so that I can discuss this with you in class. So number 1, bone marrow transplantation can be used to treat leukemia. Leukemia, I mean, there are different types, but in essence, is an uncontrolled division of a certain kind of blood cells, right? Like you have the productions of too many white cells of a certain kind, and that is, in essence, what's causing the leukemia. And so to fix that, you will have to replace the cells in the bone marrow so that you are able to create new blood cells. Okay, to replace the defective ones that are in the bone marrow, essentially. So speculate the effect of bone marrow transplantation on a person's blood type and justify your answer. When you replace the bone marrow, you are basically replacing the stem cells in the bone marrow that are giving rise to these blood cells of yours. So the rule for bone marrow transplantation is the same as the rule for blood transfusion in general. And so if you take, let's say, B blood and you give it to an AB person, right? If you do blood transfusion, if you do blood transfusion, then the cell's not gonna stay in the body indefinitely. And so, you will briefly have type B blood cells in your system, and then once they die off, then you will go back to your normal AB blood type, right? However, in bone marrow transplantation, because we are replacing the stem cells, and those stem cells are the ones that are going to be giving rise to your new blood cells, right? And the bone marrow will stay there for quite some time, right? And as a result of that, all the new cells that are coming out from the bone marrow will be of the different blood type. So that's how it is possible for someone to have a different blood type following bone marrow transplantation. Now, of course, you can take bone marrow from an AB person and give it to another AB person, right? In that respect, then you won't be changing the blood type in that case. Okay, so does that answer the first question? Anybody have a follow-up?
Yes, Professor. What is the difference between transportation and transfusion?
Transfusion, you're only giving the red cells, right? So the red cells are not going to live forever. They go into your blood and they will be there for like, a couple weeks or at best a few months, right? And then it's going to be gone. It's not a permanent thing. Okay, but for bone marrow transplantation, because you're giving the stem cells, and the stem cells have a way to renew themselves. So for bone marrow transplantation, it's more like a permanent thing, right? We're trying to cure the leukemia, right? So we need the new bone marrow to essentially replace the defective one. So that's why there's a more of a permanent change when it comes to bone marrow transplantation.
So the AB can have AB only, or they still can have A. to the
Yeah,
AB.
for the bone marrow, right? Yeah, that's right. This is also possible, right? So once you give the A bone marrow to an AB person, it's
Can they
possible for the blood type to change to A, right?
can
Yes,
they
Tahib.
give B or vice versa?
Can B give to AB? Is that what you're asking?
Yes.
Yes, that's right. Yeah, but you cannot give AB to B, right? So the rules are the same as red cell transfusion.
So then the blood type will be changing from AB to A.
That's right. That's right.
Okay.
Okay, next one. Sally's first child was born with hemolytic disease of the newborn. She learned about ROGAM from her friend. Sally is now pregnant with her second child, and she is requesting to receive ROGAM shot from her doctor. Is Sally's request valid? So first of all, hemolytic disease of the newborn is a condition where there is blood incompatibility between the mother and the child, right? And the one we talked about in class is Rh positive baby, right? And Rh negative mother, right? This can happen for other blood antigen as well, but Rh is the only one we talked about. So when the baby's positive blood enters the mother's bloodstream in the first pregnancy, for example, right? Then the mother becomes sensitized, right? Remember that note we took? Right? Let me just quickly bring that up. Sorry, my notes are like super unorganized. I put them in the wrong place. Let me see. Oh, there it is. Right here, right? So remember this picture, right? In the first pregnancy, if the placenta is damaged, then the baby's blood is going to go into the mother's blood, and the mother is going to become sensitized, right? Meaning she is going to start making anti-Rh antibodies. Right? Remember the note we took last week? Right? That whole selecting the naive T cells and the B cells, and ultimately you're going to create the antibodies, right? Except in this case, we're creating the antibodies for the Rh. Okay, so first baby is usually fine, right? If this happens during delivery, by the time the mother makes the antibody, the baby will be out already. But since she already has the antibody, in future pregnancies, the Rh can cross the placenta and attack the baby's blood, right? Causing the baby to have hemolysis. There's going to be a jaundice, swelling, right? Liver and spleen is going to be enlarged. So all these things is characteristics of hemolytic disease of the newborn, right? So to prevent sensitization from happening, you can give ROGAM, which are these green antibodies. They are man-made, they're really big, and the job is to prevent sensitization from happening. If the baby's positive cell made it into the mother's bloodstream, the ROGAM will clear all of it before her immune system is activated. That's the job of ROGAM, right? So back to our question here. She had hemolytic disease newborn for her first child. Okay, so why is that the case? Right? Based on what I just showed you in the note, shouldn't that be a problem for like second pregnancy? Why would she have a child, a first child, with hemolytic disease of a newborn? Does anybody have an idea why that might be the case?
Because she has now the Rh plus antibodies.
Yeah, but this was her first kid though, right? Why would she have the antibodies?
Because in case if she got it before the first kid, then she will never have sensitized.
If she got what's before the first kid, you're on the right
Um,
track.
the medicine, the Rogam.
Oh, no, no, no. It was, before why would she be receiving the ROGAM in the ROGAM is to prevent the sensitization from happening, right? And remember, the ROGAM does not cross the placenta, right?
Right.
ROGAMs are really big. It wouldn't be crossing the placenta. That's the whole point. Like we don't want the ROGAM to be in the baby's blood. It's gonna, hurt the baby. So my question to you guys is, why would she have the antibodies before her first child? Because that's what's happening here, right? The first child is having the hemolytic disease of a newborn because the mother already has the anti-RH in her system. I am asking you why that would happen. She didn't have a baby before. This is her first child.
She
Where?
must have got it from some other sources, from blood transplantation or anything else.
That's right. Okay, so this suggests that Sally was previously sensitized already. Okay, how? Possibly through Rh positive transfusion. Okay, maybe there was an emergency that she needed blood and they did not have O negative on hand. So they gave her O positive. Do you understand that? So she would already be sensitized. And that's why her baby was born with hemolytic disease of the newborn. Okay, so having said that, is no use to give her ROGAM. ROGAM does not reverse or cure sensitization, right? It just stops it from happening. But if it has already happened, then it's not going to fix the problem. So this is not a valid request. Do you understand that? Any follow-up question? Okay, so that's why, like in real life, right? In real life situation, if there is someone who needs blood, someone who comes in from the street, let's say, right? Like when I say from the street, I mean like, someone just arrives in an ambulance or something and they needed blood. And if it's a woman of like childbearing age, I don't know what the limit is. It depends on the hospital policy. Let's say they're before like 50 or something, right? Then you will give them O negative. Okay, if you don't have time to check anything, you just give them O negative, right? And then if you don't have O negative, then yes, you can give them O positive. Okay, but because they are of childbearing age, right? We don't want this scenario to happen. That's why O negative is the best choice, right? And that's why they call it O negative, like the universal donor, right? Because that's like the one that you give in an emergency situation if you don't have time to to think about everything. What about men? If a man comes in to the ER, they really need blood. Should I give them O neg or O positive?
Shouldn't matter if you don't have the O negative.
That's right. In fact, it's a common practice to save the O negative for the ladies, okay? And you can give the man O positive, no problem, right? Because we don't have to worry about hemolytic disease of newborn for the guy, right? Okay. Sure, we will sensitize him. So next time, if he needs blood again, we have to be careful, okay? But then, it's not a serious concern for the men as much as it is for the lady, right? I hope I'm making sense here. Okay. Anybody have any questions?
Yes, Professor. So when it's in question saying that first child was born with HDN disease, it means he's like the child has the disease.
That's right. The child has the disease. The mother does not have the hemolytic disease. It's always the child that's having the problem, right? With the enlarged spleen, with the anemia and the jaundice and everything, right? Because her antibody, like Sally's antibody, is attacking the baby, right?
Got it.
Okay. Yeah, and I want to emphasize, nobody's blood type is changing here. Sensitization does not change your blood type. Sensitization just means you will make the antibodies to attack that particular blood type, right?
So what if the blood type of baby is Rh negative? It will still affect baby?
If the baby is negative, then it's okay. Negative means there's no RH on it. Even if there's anti-RH antibodies in the mother, it's not gonna, even if it crosses the placenta, there's nothing to attack, right?
Right. So then the baby will not have HDN disease, even if the mother has sensitized.
That's right. So that's a possibility. Okay, let's say the mother is negative negative and the father is positive negative, right? If you do the Punnett square, the baby is 50% chance positive negative, and then 50% chance negative negative, right? So it's possible that she got sensitized the first time if she did not receive the ROGAM, and the second baby would have been okay. Second baby would have been okay, negative negative, right? So that's something that they have to counsel, right? Like, you know, if someone has the first child, hemolytic disease, and then they're like, okay, looking at the genetics, there's a 50-50% chance, right? So like, you know, make an informed decision, right? Okay, moving on. So these are the application question for lecture 3. At the end of last class, we talked about how we can separate active immunity into how to separate acquired immunity into active or passive. Remember, active means you have to make the antibody yourself. So it's going to take some time, but then it's long lasting. Passive means someone else is giving you the antibodies. Okay, you did not make them, someone did. Okay, they give it to you and you will have immediate protection, but it's not gonna last for a very long time, right? And then under each branch there is like, you know, natural and passive, right? So maybe, you know, just let me backtrack a little bit here. Where's the fill in the blank in this thing? Oh, right here. Okay. So why don't we just take a moment and just do these 4. Okay. Let's classify them as natural versus artificial, and then active versus passive. Let's take a look at the first one. Ronnie, age 6, has had chickenpox and recovered. He now has blank immunity. So first of all, do you think this is natural or this is artificial?
Natural.
Natural. The easiest way to figure out if it's natural or not is like, did you inject something? Right? You did not, right? Okay, so this is natural. And is it active or is it passive? Did he make his own antibodies or did someone give him his antibodies?
Active.
That's right. So this is natural active. Okay. So, you know, Madison, you said acquired immunity. Yes, it is acquired immunity, but then we got to be more specific, right? Like, how did he acquire the immunity? Did he acquire it through natural means or induced means, right? Was it like an active or a passive immunization, right? Immunity, I mean. Okay, why don't you try, all of you try 18, 19, and 20. I'll give you like, you know, 2-3 minutes and I'll take it up with you. Meanwhile, feel free to ask questions. You know, feel free to type the answers in the chat box as well, if you have it. can private message me if you don't want the whole class to see it. That's okay as well. Okay, thank you. Okay, so let's talk about them. Kathleen has been exposed to hepatitis. She will receive an injection of serum. The serum is purified antibodies, right? From someone who's immune to the not immune, for someone who has already fought off, right, the disease, in this case hepatitis, right, which will give her blank immunity. Well, I see the word injection. Anytime you're injecting something, it is artificial, right? Another word for artificial is induced. It's in the notes, you can see. Now, does she make the antibody or not? Well, we are injecting the antibodies into her system, right? The antibodies are already created. It's not hers, right? So if she didn't make it, then it's passive. Okay. So again, if you inject something, it's artificial. If you didn't inject anything, then it's natural. Did you make the antibodies? If you did, then it's active. If you did not, if someone else made the antibody, then it's passive. Sandy is going to summer camp. The physical form asks whether she has received immunization to measles and mumps. This type of immunization is, so immunization, right? Think about the yellow card for yourself or for your kids, right? That's an injection. So that is artificial. Passive or active?
Active.
This is active. So the injection contains like dead viruses, right? That will educate your immune system to prepare for the real thing. You still have to make the antibodies. That's why after receiving a vaccine of any sort, you might experience some fever. That's your innate response. That's your immune system telling you, oh, something foreign is in the system. We have to create the antibodies. All that is normal. That's part of, the clonal expansion and all the stuff we talked about. You are not getting the actual disease. You're getting part of it, the part that is not going to make you sick, but it will show you what the real virus looks like. So that's active artificial.
But Professor, we are giving the virus, we are not giving the immunity. So is it not naturally producing?
Say that one more time. If you're giving the virus, you're not giving the what?
We're not giving the serum or the antibodies. So is it not creating the antibodies naturally?
You talk about 19?
18.
18? Okay,
Yeah.
so the serum already has the antibodies.
No, sorry, 19.
19? Okay. So in 19, when you receive an immunization, you are basically giving part of a virus, right? Or part of a bacteria.
Yeah.
And your body will create antibody against that. That's why it's active, because you still have to choose the naive T cells that recognize that part, right?
Right,
And
but I'm saying like body's creating it, you are not giving any antibodies to the body. So it should not be natural.
No. Natural is not about that's not what natural means. Natural means like another way to think about this is, would this have happened like 200-300 years ago? Okay, no, right? Like it's not, it couldn't have happened because like, you know, we don't have the medical evidence to do it yet, right? Okay, whereas like catching a disease, right? Would that have happened 200-300 years ago? Yes, right? So if it would have been happened without human intervention, then that's what natural means, right?
Okay, thank you.
Yeah, yeah. So that's what I'm saying, right? If you inject something, regardless whatever you're injecting, that's not natural. Right? We shouldn't be injecting anything, you know, like naturally, right? That's why we call it artificial. Anyone else have any other comments or questions? Are you guys with me? Please let me know. Okay, like there will be questions on the test for this. Okay, that asks you, you know, pick the one that's natural passive or something like that.
So anything which has the human intervention is artificial.
That's correct.
Guys.
All right, all right. Next one. Baby Janice's mother has had mumps, which give Janice is the baby, okay? Some kind of immunity, but it will only last for about a year. So this is going to be natural and passive. Through the placenta, right? The mother's antibody can cross the placenta and enter the baby, right? The baby did not make the antibody. That's why it's passive. And that's why it's only going to last, you know, sometime. There's a time limit to it, right? All right. Back to our application question here. Joffrey is bitten by a rattlesnake while on a camping trip. His friends immediately rush him to an emergency facility. The venom is a protein-based toxin. What treatment would provide immediate protection and why?
We can give serum, which is passive artificial.
That's right. So we can give him a serum. Right, so the serum contains antibodies that will neutralize the toxin. Remember the PowerPoint slides? We talk about the function of antibodies, right? They neutralize virus and toxins, right? And they could, you know, enhance phagocytosis and all that stuff. But in the context of this, because it's a protein-based toxin, the antibodies would be a perfect choice. Okay, so this serum contains antibodies that are purified from probably not at the person to create like you know, serum for venomous snakes. I think they use animals to do it. Okay, like to purify the antibodies from animals. So explain this type of immunity. This is artificial because you're injecting something, and this is passive. That's why it has like immediate protection. If Joffrey were to be bitten by another rattlesnake in the future, unlucky Joffrey, will he be immune to the toxin?
No,
Why not?
because it's an artificial passive.
That's right. So, excuse me. Yeah. These artificial passive, it's not meant to last. Right? He did not make the memory cells. Right? He didn't make any memory T or B cells. Right? The only way for this to happen is perhaps you know, he's able to fight it off himself, but it's not realistic. Right? By the time he's able to produce the antibodies, the toxin would have probably hurt him severely already, if you know he doesn't die. Right? Oh, well, no, not on the same day. I mean, like it's still gonna be okay, right? For the serum, it's still in his bloodstream, right? So he's probably okay for the day, or yeah, short-term protection. Okay, we're talking about like couple weeks, month, even. Yeah, I asked my doctor. It was like, hey, if I, even though I know the answer, I don't know. I just feel like asking him. I was like, if I get bitten again in the future, do I have to come in for more shots? He's like, yep, yep. So you better not get bitten. Okay. But there is a time frame for which, during which you will be protected. All right, moving on. One dose of vaccine against chickenpox will virtually offer a lifetime protection against the virus, whereas a new flu shot is needed every year. Explain the reason for this. Okay, so just a quick lesson on the flu. Okay, you should write these down as well. Okay, like I'm not just like randomly telling you stuff. Okay, like these are things that are possibly important, right? Flu is caused by the influenza virus, and there are 4 types. Influenza virus. A, B, C, and D. A and B are the ones that are responsible for seasonal flu. Okay, and A is the only kind that's known to cause pandemic. Okay, anybody remember the last pandemic we had before the COVID one?
The
Some of you-
Spanish flu, early 1900s.
That's 1900. No, it's more recent. Yeah, but you got part of it right. Okay. Anybody remember? Some of you might be too young. When's the last one? Come on. Some of you must remember.
Was it SARS?
SARS was not a pandemic. SARS was 2003. Yeah, that's a pretty bad one. SARS related to well, obviously it was related to COVID, right? Because COVID is caused by the same family of virus. There is another one after 2003. No, something about
Ebola?
no.
I can't think of anything.
Yeah, there was an Ebola outbreak in Sierra Leone in 2008, I think, or 2004. I don't remember exactly, but that was not a pandemic. The last pandemic we had was 2009. Okay, that was the H1N1. H1N1. Do you guys remember that? Right? They call it the swine flu, right? The swine flu back then. Does that ring a bell? And then they told everybody to get vaccinated, and it turned out it wasn't as bad as they thought it was. So it was a short-lived pandemic. Do you guys remember this at all, or maybe?
Yeah.
Yeah.
I know.
No.
I
Yeah.
think I was in like first grade.
First grade. Yeah. So like oblivious about these kind of things, which is good, right? Like less things to worry about. Like my kids, they don't really think too much about these things. But anyway, that was the last one. Okay, so that was caused by H1N1, which is the first, like the influenza A. Okay, so the like inside these viruses, right? A and B, these flu viruses on the surface, they actually have 2 kinds of antigens. They have the H antigens, and then they have the N antigen. It's much like what we have, right? Like on the red cells, we have the A, B, right, and the Rh, right? Well, for the virus, the antigen of interest is what's called H and N. You don't really have to know what they stand for. There are 18 variants of H and then 11 different types of N. Right? And so, there are different combinations. H1N1 is one of the, the ones of concern because, in the early 1900s, as medicine pointed out, that was the one that caused the Spanish flu, which killed a lot of people, right? Anybody remember another one that you might have heard of? The bird flu. Does anybody know what that one might be? Might have read about it in the paper. Right, H5N1, right? That's like the bird flu, the avian flu. That is also quite scary. And they end up have to kill like a lot of like chickens, right? Whenever this things happens, because the reservoir of the virus is in the birds, including the chickens. So if you kill them off, then it prevents the spread in some cases. In any case, there are many different kinds of viruses. Some is more likely to cause severe outbreak than others, and so every year the World Health Organization, they monitor the trends of how these viruses are behaving, how they're mutating, and they determine the top 3 strains of flu virus that are going to be circulating in the upcoming season. Okay, like the flu season. So it's like a prediction, and then they make the vaccines for it. Okay, so whatever vaccines they make is only good for this particular season. Okay, next season there might be 3 new different strains that are circulating. Okay, and then you will have to create new vaccines for it. It's not practical to create vaccines for all the different combinations. Okay, it's like, you know, cost ineffective, and then, like, you know, your body is not going to be reacting well in that case anyways. So that's why you have to update the vaccines. And because the vaccines are a prediction, based on prediction, sometimes they are wrong, and that's why sometimes the flu shots are, you know, not very effective for a particular winter. We are kind of fortunate in the northern hemisphere, because our winter comes after the southern hemisphere, so we can always look at what's happening in Australia and see if the vaccines were doing a good job. Okay, so that's why we will see the data right before the winter season. It's like, oh, the flu shot was only 18% effective this year, because sometimes the prediction is a little bit off. Okay, Korea said something related to cows, like cowpox, maybe. I don't know what it is. I don't remember. Mad cow, yeah, maybe. Yeah. Do they have to share? What do you mean? Do they have to share? Share what?
So like if they look at like what happened in Australia, what if Australia like doesn't want to share like what happened because they just don't want to
Oh,
look
no,
bad
no,
or
no. All these things are public data. Yeah, yeah. Like because it's like such a huge thing, everybody's kind of scared of like a global outbreak. So, you know, there are mechanisms to report it to like public health, and the public health kind of submit the data. So there's like some kind of centralized, you know, situation.
Because the virus can mutate itself like COVID, it keeps on changing the mutation.
That's right. And that's why we have to keep on updating the vaccine, right? So the goal here is to create something that is for a part that is not changing for the virus. Okay. But it's hard. Think of these things as like a mushroom. Okay, a mushroom, a huge mushroom. Okay. So like the cap of the mushroom, the crown here, this part keeps on changing because of genetic you know, shuffling. The stem might not change, but then if you create an antibody, it's really hard for the antibody to like get to the stem, because like the mushroom cap is like blocking everything, right? So that's what they're trying to do. If they can come up with an antibody that targets a non-changing part for the flu as well as for the say the coronavirus, then it's possible to have a universal vaccine that you only have to get 1 dose, and then we're good for. Okay, so to answer this question, chickenpox, they don't mutate. Okay? They don't change every season. So that's why once you get the vaccine, you're protected for life. Or if you recover from chickenpox, you have the antibodies and you're protected for life. But flu virus, it changes, it mutates. So just like the coronavirus, it mutates. That's why, you know, people are very concerned that if it mutates to a point where the virus is very very transmittable and very deadly, then it's gonna have a, you know, very serious pandemic. They say this is not the big one. Like this pandemic is not the one that people have been worried about. Sure, it caused a lot of you know, economic damage, and a lot of people die from it. But they say a truly scary pandemic, it could be much worse. There's a book by Bill Gates called How to Prevent the Next Pandemic. I just read it last month. It's pretty good. If you're interested, you can, you know, look it up. It talks about all these things. All right, moving on. HIV infects macrophage and destroys them. Explain how this will affect your immune system. I forgot who asked this question, but it was like 2-3 weeks ago, and I keep on saying we're gonna look at it later on. This is the later on, okay? So the reason why the body cannot just make antibodies to attack the HIV. HIV, by the way, is the virus that causes AIDS,
I
right?
have a question also.
It was you? Yeah, okay.
So
Do you have-
is it possible to be tested negative in HIV, then the person already has AIDS?
It's possible to be HIV positive but not have AIDS.
No, like when a person is HIV negative,
Mhm.
but already when the person was tested HIV negative, maybe the person already had AIDS already. Is that possible?
Is it possible for someone to have AIDS and test HIV negative? Is that what you're asking me?
Yes, tested negative, but the person already
I
has
don't
AIDS.
think so. I don't think so. I think, for you to have the disease, your viral level would have to be at a particular level, and it would be show a positive based on what I understand. Okay.
Okay.
So why can your body fight it off is because the HIV virus actually specifically infects the macrophage. You remember macrophage, right? They like go around and eat stuff, and more importantly, they are antigen presenting cell. They are the ones that are able to select the naive T cells, which ultimately will lead to the selection of the naive B cells and then making the antibodies, right? So if they infect the macrophage, you're missing the link. You're missing the link between innate and adaptive immunity. Without adaptive immunity, you essentially lose your immune system, right? So people who have HIV, they don't die from HIV per se. Okay, they kind of die because of other opportunistic infection. Like you and I might be able to fight off a cold, no problem. Okay, we get the influenza, we can fight it off. Okay, we feel miserable for a week or so, but then we can make the antibodies. But people who have the HIV, because the adaptive branch of the immune system is down, right? They are not going to be able to fight it off, and that's why it is a deadly disease. Okay, moving on. Many COVID-19 vaccines are mRNA vaccines. I think I explained this already, right? By feeding the mRNA to not feeding it, but like by injecting the mRNA into your body, the APCs will pick up the mRNA and then it will create the spike proteins that are on the coronavirus, and then it will present it to the naive T cells, right? And then it goes through the clonal expansion, and that's how you make the antibodies. Okay, that's basically it. Any other questions before I go back to the PowerPoints? That took way longer than I expected, but that's because I talked too much. Any questions?
Test will include which chapters?
The test will be 2, 3, and 4 only. 2, 3, and 4. Okay, I can see most of you are here already. My usual 18, good students, I suppose, right? Because you guys come to class. I want to talk to you about the lab quiz. Okay, so the lab quiz is going to be due on February 6th. And you can access it here. Okay, you can access it here. Let me switch to student view. So anatomy quizzes, right? So you can see the lab quiz will be available on the 31st, which is Wednesday, and you have until February 6th to complete it. So 2 chances for the lab quiz, and only the best counts, right? Okay. To prepare for the lab quiz, though, you have to go and work on these packages. So you go to labs, and then there's the online lab. And you do not have to hand these in. You just have to do it yourself. Okay. So the lab quiz will have questions related to these slides, related to these models. Okay, just work through them. I will take them up with you possibly like maybe next class, probably not. Next class may be too rushed. I'll probably take it up with you during the test one review. Okay, we'll see. We'll see. Okay, if I don't have time to take it up, I'll post the answers for you maybe. But you have to go through it yourself first. Okay.
So you will go through after the ending date?
Sorry, what is that again?
You will go through the lab quiz after submission date?
No. I'll go through the lab quiz before your. No, I'll go through the lab before your lab quiz.
Okay.
Yeah.
Because the test quiz is 7th.
Because the lab quiz is due on the 6th, right? So
Yeah.
if I go through it on the 5th, you're still gonna have time, right? Okay. And so I heard someone else had a question.
The first test is 20 marks, right?
20%, yeah, 20% of your final grade. That's right.
Thanks.
Okay. So start the lab as soon as you can, please.
Sir,
Mhm.
the online lab that we have to go through is just the first one or all three of them?
Just the first one. Yeah, just the first one. Okay, the other two is for like unit 2 and 3, right? Okay. I suggest printing it out and then have the thing next to you, right? For reference. Most people like for real. I know some of you were disappointed with the first quiz. But seriously, the lab quiz, most people get 95 and above because you have 2 chances, okay? You have 2 chances. Don't do them one after the other. Okay. Do it first, I don't know, like in the morning or something. And then study more and then try it again if it didn't do well.
So the lab assignment, do we have to download the document before?
Yes, you have to. So for the lab activity, okay, let's just call it lab activity right here. Where is it? These things, okay? Like you can download the PowerPoints, right? But like I said, you don't have to hand these in. These are just for you. Okay, we're only doing the first one, right?
The lab quiz.
Yeah.
Sorry. Lab quiz will tell us which questions we did wrong, or it will just tell us these many questions were wrong.
No, it will not tell you which one is wrong. Yeah, that would have been like way too easy.
Is it the lab one?
Yes, the lab one. Yeah, just the lab one. Okay, here I'll hide these ones. Okay, like if it's confusing you. Maybe I'll do it later. Okay, but yeah, like it will make sense. Like if you open the second one and you see the brain, you're like, we never did brain before, right? Then you're not supposed to do it, right? Okay, I hope. All right. Here's a question. Okay. Let's see. Kind of all over the place, the answers. But let's try to break this down together. T cells are immune cells that fight infections. We know that already. There are like killer T cells, helper T cells. In T cell therapy, some T cells are removed from a patient's blood. Then the cells are changed in the lab So they have receptors that allow them to recognize the cancer cells. This is a big thing that they're doing right now, okay? And there are like a handful of successful cases, and this is the future of tailored cancer therapy. So for this to work, receptor must do all the following except 8. Recognize an antigen that is found only on cancer cells and not other somatic cells. Okay, so that needs to happen. Right? Otherwise, the T cells will attack both good cells and bad cells, and that is bad news. Okay, you only want the T cells to attack the cancer cells and not the bodily cells. B. Recognize an antigen that constantly mutates in the cancer cells. Well, that would be ideal, but that's not going to happen. Remember, the receptors are only good for one type of antigens, right? Like if we create the red one, it's only good for the red. It's not going to work for the purple, orange, and other stuff, right? So this is the exception. Okay. Trigger clonal expansion, of course, right? We need to have a pool of these T cells so that they can specialize later. And of course, produce effector cells that will attack the cancer cells. All right, so this hopefully makes sense. And there's another book that I read. It's called the Songs of the Cells. That's also very good if you are, into some reading. It talks about these T cells therapy, which are, I said, going to be the future of tailored therapy, not just for cancer, but for a whole host of other conditions. How about this? Okay. So collecting plasma, which is where the antibodies are, and if you're giving it to someone else, injecting it, this is artificial, and it's going to be passive. Okay, artificial passive. So this was turns out to be not very effective strategy because number one is costly. Number two, they were not able to scale it up for everybody, right? In a pandemic, you need to have a medication that is easily produced and be able to create it in a large scale, right? At a low cost. And this turns out not to be the case, so that's why it didn't. You don't really hear much about it. Okay. All right. So I want to ask you a question. Right? How many diseases have mankind eradicate? That's the term. Eradicate means like completely gotten rid of in the world. Okay, so in the history of mankind, how many diseases have we completely got rid of? If you think I mean, if you know what, actually, let's just end the poll. Type me a number. What do you guys think? You can give me a range. You give me a specific number, whatever you want. Greater than 10, less than 10, less than 5. What do you think? How many diseases have we completely got rid of? 0. Okay. Mohammed says 0. Anyone else? Just give me some number, guys. Okay. There's no right or like, okay, 5 makes sense. 5. Good. Other guesses? Okay, Blessing also says 0. Well, we are not that bad, okay? Like 0 is depressing perhaps, but we did okay. we did a little bit better than that, but not that much better. Okay, we were able to get rid of one disease. Okay, and that is smallpox. Right? So for those of you who don't know, so again, right, smallpox is the only disease that we were able to eradicate. Okay, it's a virus. So smallpox is a serious contagious infectious disease caused by the variola virus, which is the same family that causes a bunch of other poxes. Do you know any other pox? I mean, I have been, saying this pox.
Chickenpox?
Yeah, chicken pox, right? And more recently, have you guys heard of another pox that was kind of the scary thing, like around last year or like during the summertime on the news? Anybody heard of it? There was another pox.
I remember but cannot recall the name.
Monkey pox. Does that ring a bell, guys?
Yeah.
You remember seeing that like on the news? Yeah. So like, there are a bunch of poxes, right, that are caused by, this particular family. But smallpox is a scary one because 1 out of 3 people, and over here it says like, 3 out of 10, which is about 30%, right, of the people will die when they get the smallpox. Okay. It's a very, very deadly disease. And even if you don't die from it, some survivors are left with like horrible scars. And sometimes the scar will cause them to become blind in the eye. And just looking at this picture is like terrible thing to have, right? And so the story goes like this. There was this English doctor, his name was Edward Jenner. Many people credit him for creating the first vaccine. Okay, but as you will see, the story is a little bit cringy. So he observed that his milkmaids, these are people who milk the cows for him, I suppose. He's a pretty well-off person to have milkmaids, where he lived. He noticed that they got this thing called the cowpox from the cows. Okay, so he had a cow. Okay, the name of the cow was Blossom. Okay, and Blossom had these cowpox on the udders. The udder is where you squeeze to get the milk, right? And the milkmaid, Sarah, got the cowpox from milking the cow. Okay? So cowpox gave you these sores on the skin, these lesions, but it's not deadly. Okay? People will recover from it, and then they're okay. So he noticed, the story goes like this, right? He noticed the people who got the cowpox appeared to be immune to the smallpox. Okay. So to test his theory, what he did was he exposed the gardener's son, name was James, with cowpox. Okay? And the boy recovered. So that was bad enough, right? Like, nowadays you can't do things like these. You're gonna get like, locked up in jail, right? But back then the ethics was a little bit loose, I suppose. So infecting the cowpox sound kind of bad already, right? But then the next thing was really crazy, right? He infected the boy with smallpox, okay, just to see if he's right, right? And fortunately, very fortunately, he was right. The boy did not get sick, okay? And what's going on here is that the cowpox virus, since it's the same family as the smallpox, they share an antigen. Okay, close enough that when you make the antibody for the cowpox virus, that same antibody turns out to be effective for smallpox as well. Okay, and so that is the basis of vaccine. Right? They scaled this up, and eventually it was done throughout the world. And by the turn of the century, smallpox is completely eradicated. They keep a few copies. Officially, they have a copy in US and one in Russia, but maybe there are other copies people don't know about. And what government worry about is like a bioterror attack. right? Like someone deliberately released smallpox into the population, right? We have no protection against smallpox, right? Because we didn't get like vaccinated for it. There's no point of vaccinating against a disease that doesn't exist anymore, right? So that's why there's no vaccination program for it, and that's why if a release of a smallpox as an intentional action, that's going to cause a lot of death. Okay, so that's the story of the first vaccination, and this is the hind from the cow, the blossom I showed you, right? It was when it died, they make the leather out of the hind, and this was gifted to Canada. I forgot when, but if you're interested in looking at it, it's in the medical science building of University of Toronto. So if you're downtown, sometime and you want to check it out, um, you can go and see it. So that's basically what it is. Sometimes the cow version of a disease is similar enough for the human versions, and vaccinating it with the cow stuff, it's gonna give you protection to the real thing. Does anybody have like a scar like on their arm here, like from vaccines when they were young? Usually people from
Yes.
yeah. I have one as well. Do you guys know what that is for? Anybody?
TB vaccine?
Yes, TB. Okay, TB. TB is tuberculosis, okay, which is caused by bacteria. The vaccine that you got that gave you the scar is called a BCG vaccine. Okay, BCG vaccine. And it's funny, based on what I read, is that the scar that you get is like it's like a sign, a confirmation that the vaccine actually worked. Okay. My scar got really, really bad afterwards. I don't know what happened. I have this big, like it's as big as this, okay, my scar, and it's like bumpy. So I guess it really worked on me. But this one is a cow version, okay, of the bacteria. Okay. And it's a live vaccine, so it's not suitable for like pregnant people or people who are immunocompromised. But when your body makes the antibody for the cow version of the disease, it actually protects you from the real one as well. But there is a problem with this. Do you guys know how people test to see whether you have TB or not? Because TB can hide in your immune system for a long time, hide in your lung before it activates. It can become dormant for many, many, many years. And in Ontario, if you want to work as a teacher in high school or in elementary school, you have to get tested for TBs. Right. So I originally wanted to become a high school teacher, right? So I went to do my TB testing. But for people who have received the BCG vaccines, they will always test positive, okay? Because of the immune response you have against the vaccine, right? So I always get tested positive, and then I have to take an X-ray to show that I actually don't have TB. And I thought, that was just like not worth it for me to always have to go take these X-ray. And so I became the college teacher, and they don't make us screen for TBs. But yeah, if you have the BCG vaccine and you ever need to get tested for it to do the skin test, you always get tested positive. Okay, a few other stuff here before same for you, Julian. Yeah, exactly, right? So you know the hassle. All right, let's go through a few other immune problems here. Anybody know what's wrong with the hand here? Like, obviously it's crooked, but what disease do you think this is? You might have heard of it before, or know of it.
Arthritis.
That's right. Okay, and this is not the kind of arthritis that people get when they get older. That's called osteoarthritis. This one is called rheumatoid arthritis. Okay, this is when your immune system attacks the joint, and it's very, very painful. Okay, so why would the immune system attack yourself? Well, we're gonna look at three situations here. We're gonna look at overreaction, from the immune system. We're going to look at underreaction. Okay. And then we're going to look at wrong reaction. So what happens if your immune system is overreacting? What if it's underreacting? And what if it's like, doing the wrong kind of reaction? Okay, I'll give you 3 examples, one of each. First one, overreaction. Okay, this is a nuisance for most of us, okay, during allergy seasons. Okay? Allergies are basically hypersensitivities to things that are normally harmless to the body. Things like pollen, things like animal hair, right? Dust mites. These things typically are harmless for the body, but for some reason, our body are overreacting to it. Okay, and when we react to these things, your body releases histamines, which then cause some of the annoying allergy symptoms: the runny nose, the watery eyes, the itchiness, right? All these things, in part, has to do with histamine. Even though allergies are annoying, they might give you like rashes and hives, but they are generally not deadly unless you have the severe form, which causes your body to go into what's called anaphylactic shock. Okay, anaphylactic shock is a rare situation where the person is extremely allergic to things like nuts, right? Like peanuts, right? Bee sting, or even medication like penicillin. Okay? These things trigger mass release of these histamine throughout the entire body. And as you learn from me, histamine will do vasodilation, right? As well as make the blood vessel more leaky. So when you have a lot of histamine in the body, it causes fluid to leak all over the place, and it causes your blood pressure to drop to a dangerous level. Okay, and a person with an anaphylactic shock could die within the hour if no intervention is provided. Okay, the airway is gonna narrow, they can't breathe, and then the blood pressure is gonna drop so much that it's not gonna have enough blood circulating in the body, and then they could die. And so people who know that they have these kind of serious allergies, they have to carry the EpiPen, which you probably might have heard of as well, right? Kids particularly, if they're at school and they have these anaphylactic shock problems, they have to carry an EpiPen, right? The people have to know how to use the EpiPen, right? The teachers and the staff. And the EpiPen basically contains epinephrine, right? Which is something that your body naturally makes, and it will reverse the effects of histamine. Okay? Epinephrine is basically the same stuff that you secrete when you're in danger or when you're excited, right? Another name for epinephrine that you might have heard of is adrenaline. When you have the adrenaline rush, your heart rate goes up, right? Your blood pressure goes up, your blood vessel is going to constrict, right? So essentially, it's going to be reversing the histamine effect. Okay, EpiPens are very expensive though. Okay, and there was a shortage a couple years back, just right before the pandemic, and people in the U.S. were coming up to Canada to buy it because there was such a shortage, which is crazy. Talking about allergies, this one is interesting. It's just for fun, I'm telling you. Hey, if you get bit by this particular tick, okay, this tick is called the Lone Star tick. You can search it up on YouTube if you want. Okay, if this thing bites you, then you will be allergic to meat for the rest of your life. Okay, you're gonna have to become a vegan. Right? So every now and then you would hear I would see some clips on the news saying, some hunter was like hunting for deer or whatever, and then they got bitten by this thing, and then afterwards they interviewed the guy. The guy was like, he was very sad. He said because he store all these game meats, right? All these meat that he hunts for, and now he can't eat it because like the allergy is gonna kill him essentially. It was discovered in Texas. Yes, that's why it's called the Lone Star tick. Okay, but I think it's not just Texas. It can happen in other regions as well. I didn't really look up exactly the geographic location, But I thought I'd share this with you because it's quite interesting. And the mechanism of how this happens is also quite interesting. All right, moving on. That was the wrong kind, sorry, that was an overreaction, right, of your immune system. Next is the wrong kind of reaction, right? When your T cells or when your immune system cannot distinguish between self versus non-self, then you end up attacking your own body, right? Remember, the T cells is supposed to pass a tolerance test in the thymus, right? Only 5% of them are supposed to come out, right? So if a T cell that recognize your own cells accidentally came out, then it's gonna attack your own body. Right? There's some genetic basis to this. Some people with a certain genetic makeup are more susceptible, more likely of developing certain kinds of autoimmune diseases. So example of autoimmune disease that you might have heard of includes things like multiple sclerosis. Okay. I don't know if there's anything else you've heard of here. Psoriasis maybe, right? Vertigo, Graves' disease, right? ALS you might have heard of. What's a famous person that has ALS? Do you guys remember? Do you guys remember like the ice bucket challenge several years back where people were raising money for ALS? Does anybody know a famous scientist who has ALS? He's on a wheelchair and he talks to a machine. Stephen Hawking?
Stephen Hawking?
That's right. That's right. Okay. So maybe you've heard of that. Anyway, so these are all autoimmune diseases where the cell attacks your own body. Graves' disease is the example I have here. These are autoreactive antibodies that binds to your thyroid gland, and it makes the thyroid really, really big. Okay, so you get goiter, and then it causes your metabolic rate to be out of control. Right? You're gonna have very high metabolism. You burn everything that you eat, so you have severe weight loss, rapid heart rate, and then your eyes is gonna pop out a little bit. I'm sorry, like that was a bad description. I mean, like your eyes gonna bulge out a little bit. Okay, like this picture, because those antibodies will bind to the muscles around the eyes and cause a constant inflammation. Okay, so autoimmune disease. The last example is immunodeficiency, which is underreaction. Okay. So immunodeficiency can be primary, which is something that you're born with, or it could be secondary, which is something that you get infected with. So HIV is an example of secondary immunodeficiency. Okay, the HIV virus caused the person to have no adaptive immunity because they kill off and infects and kill off the APCs, right, the macrophage. So you cannot mount an effective immune response. But there are good cocktails of medication nowadays to help manage the disease. Primary immunodeficiency or immune deficiency is something that a person is born with because of genetic mutation. And one that I usually tells the class about is this thing called SCID, severe combined immunodeficiencies. Okay, SCID. Anybody heard of the story of the bubble boy by chance?
Yeah.
Yeah, bubble boy. Okay, so just very quickly, these people who are born with SCID, they have zero immunity. Okay, they would die just by exposure to airborne pathogens. So for the longest time, the only way to protect them is to have them in a sterile bubble. Okay, so the person would have to live and grow in this sterile environment. All the stuff that you give them has to be sterilized, the food, the water, and the parents cannot physically touch them. Right? You see in this bubble there are these holes. That's for the parents to like stick their hands in and to interact with the kids with gloved hands, basically. So you can imagine that is a terrible way to live, right? For the boy as well as for the family, right? It's a terrible thing to not be able to hold your own child, right? And there was without treatment for a very, very long time. So there was actually a movie that was made about the bubble boy. That's what they're called. This person is called, and you know, sometimes it's called the bubble boy syndrome. So long story short, when the boy, I forgot what his name is, but when he was around 11, they were able to do a bone marrow transplantation for him, using the bone marrow from his sister. Okay, so the bone marrow transplant would work because then the stem cells is going to be able to make new immune cells, right? New white cells, which is what he was lacking, right? But the problem was, you know, he actually got better initially after the transplantation, but you know, shortly after, within a few months, he died of leukemia. And what happens is there is a virus called EBV, and you can look it up if you're interested. And EBV can hide in the bone marrow. And what happens is, when the immune system is weakened, the EBV can activate and it causes leukemia. So this EBV was hiding in his sister's bone marrow, but because she was having a normal immune system, it was able to keep the virus at bay. But when they do the bone marrow transplantation, the EBV got into the boy as well. And even though he was starting to make immune cells, it was not enough to suppress the virus. And that's why it caused it, the problem. Okay, so nowadays they are trying to use gene therapy to cure SCID, and there are a few successful cases. So maybe in the future, this would not be a problem anymore. Finally, AIDS, I told you about. It is a virus that is going to be able to infect macrophage and APCs. And even if you're able to get some helper T cells out, they will infect those as well. And that's why it's a crippling a condition that completely takes away your immune system. There is a mutation, and I'm not going to go into too much detail. Okay, there's a mutation called CXCR4, which, if you have that mutation, you will not be infected by HIV. You're immune to HIV because the HIV does not recognize this protein, and they need this protein to go into your cells. Okay, so there was a case where a man had HIV. Timothy Ray, that was his name. You can look him up if you want. And he needed a bone marrow transplantation for some other reason. I think it was leukemia. And what happens was that the donor of the bone marrow happened to have this mutation. And so in receiving the bone marrow transplantation, not only he was able to fix the leukemia, he also turned out to cure his AIDS as well. Okay. So for the longest time, this was the only case because this mutation is super, super rare. And for the person to also be a compatible bone marrow donor, it was virtually like, you know, 1 in billions of chance, right? Okay, but since then, I think there are 2 additional cases where this has happened. Okay, so that's an active area of research. Okay, so last poll questions, and I'm going to give you a break. Okay, which of the following is an example of autoimmune disease from this list? Okay, what do you think? All right, I think I'm gonna close the poll. Hopefully you chose Graves' disease. Okay, anaphylactic shock is allergies. These 2 are immunodeficiencies. All right, that's it. Why don't we take a 10-minute break? Okay, I feel like Well, I've overwhelmed you with so much information. Let's take a 10-minute break. We'll resume at 10 o'clock, and then we'll do an hour of lecture 4. Okay, so see you in a bit. We will also be coloring the stuff from the study guide. So if you're able to get a digital copy or physical copy, even better. Right? So see you at 10 o'clock. Hello again. Let's move on to lecture 4. This is probably the easiest lecture out of the unit. If you survive the blood stuff and the immune system, this should be relatively okay. So respiratory system. We have a healthy looking lung right here on the left side, and this is smoker's lung. And you can see not only are the lungs being affected, but the heart is also being affected. Okay? Because one reason is because when the lungs are affected, you're not able to distribute oxygen efficiently in the body, and your heart muscle gets bigger to try to compensate for that. Right? So we call that hypertrophy. More on that at the end of the lesson. Let's start with some basic stuff. What's the purpose of breathing? Well, breathing gets oxygen from the air all the way to the cells. And at the same time, we're going to be expelling, removing carbon dioxide from our body. So it turns out there are multiple barriers that the oxygen has to cross before making it all the way to the cells, to the tissues. First of all, exchange between the environment and the lungs, that is called pulmonary ventilation. Okay? Pulmonary ventilation, right here. Okay, and once it gets into the lung, you have to do diffusion between the lungs and the blood, and that's called external respiration. And then the blood will carry the oxygen to the tissue, where you will have internal respiration. Okay? So the act of breathing in and out only gets the oxygen to the lungs. Right? So that's pulmonary ventilation. Then when you have the pulmonary arteries going to the lungs, you performing that pulmonary gas exchange, that is external respiration. And then the systemic circuit would distribute the blood to the tissue for internal respiration. Of course, the whole point of doing this is so that we can do cellular respiration. This happens inside the cell. You learned about this last semester, how we convert glucose and react it with oxygen to produce carbon dioxide, water, as well as ATP, which is what keeps our cell functioning. Right? Now it's a long way down to the lungs, and there are several key structures that we pass through. Starting at the top, we have the nasal cavity, right, the pharynx and the larynx, which I'll explain to you in great details coming up. Right? But that's the cutoff. That's the cutoff for the upper respiratory tract. When you have an upper respiratory tract infection, it infects these things. Okay, so we're talking about the flu, right? That's upper respiratory tract infection. You're getting a cold. Right? So these things you tend to recover quite quickly. When you have a lower respiratory tract infection, it includes some of these deeper structures. So things like pneumonia. In some cases, COVID can cause quite a bit of damage in the lungs, right? Tuberculosis, all these things take quite some time to recover, right? Because the structure affected are deeper inside.
Sir,
Yeah.
what about asthma? Is that a
Asthma is not an infection per se, but as you will see, asthma affects some of the things inside the lungs called the bronchioles. We're gonna get to it, I promise.
okay.
All right, so I want you to take out the study guide. I know not everybody has a printer, and that's okay. You have to find your own way to study these things though, okay? So please go to this guy, okay, this diagram. Okay, I just want to go through several things with you. You know, if you have it on your computer screen, you can maybe point things to it. You know, whatever way works best for you. All right. So over here, can you guys see my mouse? Okay, yeah, sometimes it's there, sometimes it's not. All right, so this is a mid-sagittal cut. Right, cut it right down the middle, and then you're looking at it from the side. Right. So here, A, right here, not is. You can put it down at the bottom. Okay, I'm just gonna put it up here because it's like I don't want to move up and down. This is the nasal cavity. Okay, nasal cavity. So, you know, just to give you a perspective, like if a person picks the nose, right, that's what they're touching. It's just right that area. And when you do the COVID swab, it goes all the way up, right? And that's why I feel like we're poking at your brain, right? So it's really spacious in there. It's like really opens up. And there's a lot of mucus and blood vessels, blood capillaries in the nasal cavity. The purpose of the nasal cavity is to help you warm. So warms, filters, there are a lot of hairs in there as well. And moistens the air. Okay, like in the winter, it's really dry. You want to add some humidity to it. If we constantly breathe very dry air, it irritates our throat. We cough a lot, and you know, it just hurts the lining. So by adding a little bit of mucus, moisture to it, you know, it just helps us feel a little bit better. So that's the function of the nasal cavity. Okay. Now, the nasal cavity opens up to a few sinuses. Okay, so there's the frontal sinus right here that you can see. There's another sinus here. And then there are a few, two other ones here and here. We don't have to know the names. Okay, sinus are just like empty cavities that are found within the bones. So when we go to the bone units later on in the course, you will know, oh, this is called the frontal bone. And that's why the sinus in there is called the frontal sinus. So I just want you to be aware that there are sinuses that you can gain access to through the nasal cavity, but you don't have to memorize the name. So when the air comes in, right, when the air comes in, some of the air is gonna go into these sinuses, and it helps you warm them up, moistens them, adds a little bit of humidity to it, right, and filters them. That's why when you have a cold, you sound different, because all these sinuses are plugged with mucus, right, and you sound like you are talking, you know, underwater or something, right? Like your voice is very deep because it's not really resonating through these structures as it used to.
Sinus is the empty cavity between the bones.
Within the bones, yeah, within the bone. Okay, so like you see this is totally inside the bone, but there are access points through the nasal cavity, so the air comes in and then it's able to go, you know, kind of take a twirl, right, in the sinuses, and that's where you will be, you know, warming them, filtering, and moistening them. Okay, the pharynx. The pharynx is the throat, basically. Okay, throat. Right? But it is the common passageway of food, liquid, and air. Everything we swallow, everything that we inhale, it's gonna pass through the pharynx, the throat. Okay. So let's take a look at the things that we breathe first. Okay. Yeah, obviously we can breathe through our mouth as well, but you know, let's just keep it simple. Let's just say we breathe through the nose. Okay. It's gonna go in, and then it's gonna enter the pharynx through this opening, and then it's gonna go here. Okay, that's the path for air. right, I'll give you a moment to catch up.
And the back one is for food?
Yes. Yeah. Yeah. Okay. So this opening here for the air to go through, this is called the nasopharynx. Nasopharynx.
Which opening, Professor?
E. You see, there's an opening here, right? The air passes through. Oops. Passes through the nasopharynx, right? Okay. E right here. Right? I'll tell you where it goes later. Let's do the food. The food. Okay. Food or liquid. Okay. Put in your mouth. Okay, and then you swallow it. It's gonna go through this opening here, F, and then it's gonna go down here.
I have two questions.
Sure.
So can the air go through like any level there on the nasal concave?
Uh, what do you mean? Any level there? Come
So it
again?
looks like there's like bottom level, the middle level, and the top level. Or I don't know if that's just how the picture looks.
The EFG you talking about?
The superior, middle, and inferior nasal concave.
Oh, you're looking at the PowerPoint. Is that what we're talking about? Like on the
No, it's
PowerPoint?
on here. It's
It's on there.
like the three ridges. I don't know how to explain it. Right? And I think
Sorry. Yeah, I didn't see it.
yeah.
No. That's just the foldings in the nasal cavity.
Okay.
Because the folding maximizes the surface area, right? So the
Okay.
air can pass through more surfaces, so you have more efficiency in moistening them and warming them, right?
Okay.
Yeah. So they
And
are
then
just folds, literally like foldings.
okay. And then the second question was, so for the food and liquid, if it like doesn't make it all the way to the back one, it can go into I think that's the trachea.
That's right, and that's like people say it went down the wrong tube, right?
Yeah.
That's the wrong tube. And what happens when the
Uh,
food goes down the wrong tube, huh?
goes into your lungs and you start coughing like crazy.
Yeah, I think it would make it all the way to the lung per se, but you know, it's gonna cause you to have a coughing reflex, right? And you know, if you don't cough it up, then the person chokes, right? Okay, so F here is the oropharynx. Okay, so there are two ways to enter the throat. You can enter through the nasopharynx, or you can enter through the oropharynx, depending on what you were like, you know, bringing in, right? Okay, so take a deep breath. It goes through the nasopharynx. Okay, if you know drink something, right, then it's gonna go through the oropharynx. So far, so good.
Yeah.
All right. Now, to leave the pharynx, if we talk about the air, to leave the pharynx, we're gonna go through this structure called G. Okay, that's like this part right here. I don't know if you can really see it on the diagram. And that is I always spell this wrong. Just let me spell it out first. So it's called the laryngopharynx. If you have trouble pronouncing things with a Y in it, just change it to an I. Okay. So if you change it to a Y, change the Y to an I, you can see it's called laryngo, right? Laryngo. So that's a laryngopharynx. Right? So the air will go through the nasopharynx into the pharynx and then exit through the laryngopharynx. Okay? That's what it is. Now, where does the laryngopharynx go? Okay, the laryngopharynx, as the name implies, is gonna take the air to this region here. Okay, I'll show you a bigger version of that later, but C is the larynx. Larynx. The larynx, Again, I'm sorry, more details to come later. But that's where you contain your vocal cords. Okay, that's where you can make sound, right? Okay, there are two things I want to talk about briefly here, and I will come back to it on the PowerPoint slides. Again, my favorite prop, right? This is the airway, right? The airway inside here. Okay, the hole that leads into the airway, the hole that leads into the larynx, that hole is B right here, and that's called the glottis. Okay, glottis. Okay, it's the opening to the larynx. Okay. And then D is the trachea. The trachea. As far as the food goes, running out of color here, it's gonna go down the tube behind the trachea. Anybody know what that's called? What's the tube that takes the food down, huh?
Esophagus?
That is right. That is the esophagus. All right. So any questions about this picture?
I thought the glottis was the epiglottis.
No, we're gonna get to the epiglottis later. The epiglottis is gonna cover up the glottis. Okay.
Okay.
Yeah. Think of the epiglottis as the toilet seat. Okay. And then the glottis is like the the hole. Okay, the bowl. I don't know if that's a on the spot analogy I can think of. Not sure if it's a good one.
That
Any
actually
other?
helps.
Okay, thank you. Any other questions for this picture? Again, we're gonna talk about these structures in detail. I just want to give you an overview, okay, of where things are.
Is the glands part of respiratory system?
Is the gland part of the respiratory system? Which gland?
The one near the nasopharynx.
The one near the nasopharynx. Nasopharynx is here. Which gland? I'm sorry.
Like, is there any glands involved in the system?
Oh, no, no, no.
Okay.
But there's like some tonsils, right? Remember we talked about tonsils?
Yeah.
Yeah. Okay. Let's go back to here. Everything is labeled here, color version. I took away the foldings, right? That's why I didn't know what we were talking about. That is because I usually take it away. I should have taken it away from the other one, the nasal conchia, but that's okay. All right. So back to the nasal cavity. I already told you, right? It warms, moistens, and filters the air that we breathe, and there are some ducts that allows the air to connect to these sinuses, right? So not only does your doctor check for swollen lymph nodes, sometimes they press, right? They press here, here, and here, and here, just down the middle to see if it hurts, right? If your sinus is like, infected or stuffed, right? That is a sign of infection, right? And the sinus is aligned with mucous membranes, which warms and moistens air passing through them. This is self-explanatory. Okay, and these
I
are
have
the
a question.
names. Yeah.
What is stuffed in them? Like when you said stuffed.
Oh, like mucus, right? Like when the cold virus infects you, your body produces. That's why you have to blow your nose and stuff like that, right? So all that extra mucus is like stuffing the frontal, like all these sinuses. And you sound different because it's kind of like the difference between singing in the shower and singing in the closet, right? Like people likes to sing in the shower because it sounds nice. The voice, your voice bounces off the tiles and it kind of resonates and give this crisp sound. But if you sing in the closet, it sounds terrible because all the clothing is muffing up all the sound, it's sucking up all of it, right? So that's the difference between when you have a cold and all your sinuses are stuffed versus when you don't have a cold, right? In any case, let's take a look at this. What do you think? Okay. So if you go back to here, you will see lyrics and above is upper respiratory tract, and trachea and below is going to be lower, right? So this one is looking for the lower respiratory tract, which includes the trachea and the bronchus. Okay. The glottis is above the larynx, right? So pharynx, larynx, and glottis is upper respiratory tract. You can't really infect the glottis anyway. Like glottis is just a hole. It's like there's nothing physical there, right? Okay. I did not mention about this because I forgot to, but I can quickly show you, okay? Like if you push your tongue up, this whole thing is your tongue, huh? It's really big actually. If you push your tongue up now, you will hit something hard, right? Okay, so that thing you're touching with the tongue is this part here. That's called a hard palate. Okay? It's made up of two bones, which you don't have to know at this point, that separates the nasal cavity from the oral cavity from the mouth. If you curl your tongue back a little bit, then it feels softer, right? Like there's this like softer part, I suppose, at the back, and that's the soft palate. Okay? And then at the end, there's a little thing that dangles. Remember that picture I showed you with the tonsil last time, and there's the thing that was dangling there at the back. That's the extension of the soft palate, and that's called the uvula right here. Okay? So when you swallow, the uvula is gonna flip back and it seals the nasopharynx. So the food's not gonna go up. Okay, food's just gonna go down. If you remember when you're younger, right? Or like your kids might do this. If you laugh while you're trying to swallow something, right? Then the food might come out from your nose, right? Okay, that's because when you're laughing, the uvula is not making a good seal, and the food's gonna come out. Can I break what? Madison? The bones? Are you talking about? The hard palate. Yeah. No, usually not. But the as you will learn from the bone unit, the part of the front here, that's the same bone that makes up like the socket for your upper row of teeth. Okay, so I suppose like if you have a really big force here, then it could break part of the bone. But typically like you cannot. It's not like you can eat something really hard and break the hard palate. That would be terrible to imagine. I don't think it happens. Okay, so which of the following separates the nasal cavity from the oral cavity? Hard palate. All right, moving on. Okay, pharynx. We wrote this down already. Let's just talk through it one more time. It is the common passageway for food, water, and air. Everything you eat, everything you swallow and breathe in, it's gonna pass through the pharynx. The air will enter the pharynx through the nasopharynx, right? And then it will leave through the laryngopharynx to go to the larynx. And food and water or other things that you drink, it's going to go through the oral pharynx, and then it enters the esophagus. Okay, esophagus is behind your trachea, behind your airway. We talk about tonsils and the lymphatic system. You have one at the very back of your nose, right? That's the adenoid tonsils, which will help screen the things that you're breathing in. At the base of your tongue, you have the lingual tonsil, and at the back of your throat, where the food enters to get into the pharynx, at the oral pharynx, you have the palatine tonsil. That's the one you can see in the mirror, right? Okay. Can see this in the mirror. That's the one I showed you before. Okay. You can't really see this one. This one, you're gonna probably have a gag reflex if you press your tongue too hard and pull it too far out, right? Okay. But the tonsils are there to screen for pathogens, for things that we inhale or swallow. Okay, so this is the larynx. And the larynx is where you can, where you have the vocal cords in them. Okay, the vocal cords. I think I have a slide for the vocal cord later. Yeah. So we'll talk more about it later. But the opening that goes into the larynx is the glottis, right? And then there is a flap called the epiglottis. Epi means on top, right? So this flap is a cartilage flap that will close the larynx when you're swallowing. Okay, so I want you to put your hand in your neck here. Okay, and I want you to swallow. Okay. How do you feel? Like, what does your hand feel? What kind of movement does your hand feel when you swallow? Anybody can give me a brief description? It's okay, your camera is not on. You can try it out. Okay, just put your hand there and then swallow. How does it feel? Oh, someone said up and down. Yeah, exactly right. You feel something pushes up, right? And that's what happens. Okay, so there is the epiglottis, and when you swallow, the larynx actually pushes up against the epiglottis, and then it gets sealed. Okay, the epiglottis actually doesn't really move. Okay, it stays in place, but it's the larynx that pushes up and seals it. Okay, you want to remember this. I think there's a question on that in the test. So let's take a look at a couple of bones that surrounds the throat area here, and there's another picture in the study guide here. Okay, so I'll give you a moment to find that, and you also have a model of this in the lab exercise. Okay, so over here, in case you're wondering, I means inferior, superior, and this is just left and right. So at the top here, we have the flap. The flap. This is the epiglottis, which seals the glottis during swallowing. Okay? During swallowing. So it prevents the food from going down the wrong tube, right? There is a bone here to help stabilize the throat. The throat is actually very vulnerable. Okay, like in movies, right? You see people, hit the person with the throat, and then the person's like, oh, I can't breathe, and then they pass out, right? It's actually true. If you hit here with enough force, it will cause swelling that would narrow your airway, and you could literally, cause someone to die because of that. So it's a very vulnerable location. But there are some bones there to help stabilize it and protect it. And this one here is called the hyoid bone. Hyoid bone. For male, both females and males have this bone, but it's more prominent in male. Okay, this bone is called the thyroid cartilage. It forms the so-called the Adam's apple, right? That the thing here that you can see in men. Female also have the thyroid cartilage, but it's just less prominent. We have another bone here, cartilage here. Why is it less? I don't know. It's one of the mystery of difference between male and female. But I can tell you that's part of the reason why the pitch of the sound is different, right? Generally, the deeper voice versus the higher pitch voice, it's because of the thyroid structure. So this is called the cricoid cartilage. So try to identify these things when you're looking at the model in the lab. And then further down, we see some rings here, which I'll talk about later. But these are rings that are surrounding the trachea. And they're made of cartilage. All right.
I have a question.
Yeah.
Why is the second to last one, like the middle one, have like that split kind of in it?
This one?
Yeah.
Yeah. As you will see, the ring is not a full circle ring. There's some gaps in it because like we don't want to. Can you remind me what's behind the trachea?
The esophagus, right?
That's right. So you don't want to like clam onto the esophagus and inhibit restrict the swallowing as well, right? So these rings are not like full circle. So there are some gaps here and there. Okay, it's not uncommon. Okay, good. Very observant. Let's go back to here. I mean, everything is here, but like sometimes I think coloring is a good way to learn. Okay, so there is the epiglottis. This is an X-ray. You can see the epiglottis right there. Let me see if this link works. Oh, I gotta pause the recording first. Otherwise, it's gonna be like, say I have copyright material. All right, so we have the vocal cords inside the lyrics, and they are two pieces of like stretchy elastic ligaments, and it's skeletal muscle, because you can control when to speak and when not to speak, right? You can control the pitch of the sound, right? All that stuff, it's basically controlled voluntarily, okay? And when air passes through the vocal cords, they vibrate and it creates sound. If there is no movement of air, you cannot create sound. And this is something I want you to try again, right? Many people don't really know this, or they don't really think much about it, but it illustrates your point. I want you to close your mouth and pinch your nose and then hum your favorite song. Okay? Close your mouth, pinch your nose, and try to hum your favorite tune. You can't, right? Okay? There's no sound at all. When you close all the opening, air is not moving in, it's not moving through the vocal cord. When nothing moves through the vocal cord, when no air moves through the vocal cord, you cannot create any sound. Okay? So here's the thing. If you don't talk, then air is not coming out and air is not going in, right? I mean, you can breathe for sure, right? But then if you're trying to talk and swallow at the same time, that's when people might choke. Because when you're talking and when you're swallowing, if that happens at the same time, the air is trying to come out when you talk, and when you're swallowing, the larynx is trying to get covered by the epiglottis. But if you're talking, then you don't have a tight seal because air is trying to come out and make sound, right? So that's when the food can go down the wrong tube. All right. I'm going to show you another picture, another video of the vocal cords here. Yeah, I gotta have to pause the recording. Remind me to record again if I forgot afterwards. So what happens if things actually go down the wrong tube? Then you choke, right? What's a universal symbol, gesture, I guess, for like, I'm choking. Well, it's like this, right? Okay. But here's the thing. People don't like full out choke um out of nowhere, right? Like if you're eating beside someone and then the other person is like, coughing a little bit, that's usually like the beginning of like something that could be wrong. So like they would like that, and then they feel like touching their throat a little bit, right? So what you should not do is what my grandmother used to do when we as kids, when we like choke a little bit, cough a little bit, they start patting you on the back, right? Like I don't know if you have parents who do that to you, or like if you do that to your kids, don't touch them, okay? Let them cough, because when you pat them on the back, the force might actually encourage whatever is there to go further down, right? The coughing is like the pressure trying to dislodge that thing for you, right? And if you ask the person, like, are you choking? And the person is able to tell you, yes, I'm choking, then they are not choking. Okay. Choking means your airway is completely blocked. And as I just told you, if you pinch your nose and close your mouth, no air goes in and out, you actually can't make any sound. So if your airway is actually blocked, the coughing would not be happening at that point, and the person would not be able to respond to you verbally, right? Okay, so like, are you choking? And then they're like that, right? Then they are choking, right? Okay. Then if you have your CPR training, which is something you would need if you want to become a nurse, right? You would perform the Heimlich maneuver on them, right? The point is to create enough abdominal pressure to push air out so that you dislodge whatever is stuck in your throat, right? Okay. And if you're by yourself, to save yourself, you will have to use the back of a chair to apply the force, right? And hopefully you're going to be able to dislodge that. This is always like a scary scenario for me. Like, in my mind, I run through the scenario. If this happens to me, like, do I use my remaining strength to like call 911, or like do I throw myself onto a chair and hoping that I'll be able to dislodge it? I don't know. It's a tough call. I hope I'll never have to find out. But that is called a Heimlich maneuver. Before I was a teacher, I used to do research at Sick Kids Hospital. I did like brain stuff. Okay. Anyway, at their first floor, there are a bunch of these framed items that are hung on the wall. Okay, and these are things that doctors have taken out from the air passage as well as the food passage from kids over the years. They've collected it and then they frame it and put it on the hallway. I always found it so like weird and amusing at the same time. Like, look at that, like a pin, right? Like I'm sure when they swallow it, it wasn't open. Okay, like that part I'm sure. I'm just thinking they open it for like visual effect to scare parents, right? So I remember at the time I was not a father yet, and I look at this thing, I was like, what were people thinking? Why would they give kids like access to these things, right? Like, buttons and all this. It's just like irresponsible. And then I became a father, and I totally understand how this is not the parents' fault, because kids they literally put anything in their mouth. Another short story, okay. I had this stress ball. It was like a blue stress ball, the ones that you squeeze on. And my younger one, at the time, she was just starting to have her first tooth. Okay, so this is like under 1 year old, I think. And she was teething and she was like always gnawing on things. And then one day I was just cooking in the kitchen, and my wife just came back from work, and then she came downstairs, and she was like, "Oh my goodness, look at this!" And then I was like, "What?" And I turned around, and then a good chunk of the stress ball, like I don't know, it must be like a little bit less than a quarter, I would say, was gone. Okay, like she ate it. She was chewing on the thing and then she swallowed. And then we kind of freaked out. I was like, oh my god, is that thing like toxic? Like, should we take her to the ER? Like, what? And then we're like, but what are they gonna do, right? They can't like flush it out or anything, right? So for the next couple of days, we were like a little bit worried, and we keep on checking her diaper to see if there's like blue bits in it, right? Anyway, eventually I think she was okay. Like, we didn't see anything come out, but it was probably there. But she didn't show any symptoms or anything that was out of the ordinary. but after that incident, I understand, right? You know, you can't really stop kids from putting things in their mouth. But safety pins, that's the scary one. Yeah, you should leave the safety pins out of kids' reach. Anyway, if you ever in downtown, you can just go into the hospital and then try to find this on the first floor. They used to keep it above the rotunda. Okay, maybe you can go take a look. Hopefully you're not there because your kids are sick, but anybody can walk into the hospital, right? And then you can go find it. All right, moving on. We have a few two concept check questions here. I think I'm just going to tell you the answers. The vocal cords are found in after everything I told you. Hopefully you know it is in the lyrics, right? People confuse between pharynx and lyrics, and the way I try to remember them is, the lyrics. Think of how you sing a song, like la 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 la, right? So that's where your vocal cords are, right? Lyrics. Whereas the pharynx is the throat, right? Okay, how about this one?
C.
That's right. It is the thyroid cartilage. Yeah, the thyroid cartilage. C. It's more prominent in male than it is in female, and only after puberty, right? Okay, let me see if we should go on here. Let me see how many more. I think that's a good place to stop. I know we still have 10 minutes, but I know I give you a lot of information today already, and this is quite short. We will be able to finish this for sure on Thursday. And if you may please do the lab exercise before Thursday, sorry, before Wednesday, that would be ideal. Okay, I want to try to take it up with you, like this lab thing, on Wednesday. Okay, but I want you to try it out first. That's the whole point, right? The whole point is for you to go through these things and try to see if you can do it.
Can we access it now? Because you said it will be visible from 31st.
No, that's the quiz. The quiz
Oh.
is going to be available on 31st, right? Okay, but the
Okay.
file, the lab file, is available now. I'll post a link to this in today's announcement. Okay, but if you go to content, it's just under the lab, right here, the lab. All right. So that's it. Thank you. I will see you all on Wednesday. Have a good day.